So now equals mc squared. So we now can add one more to our list over here. Now I do want to throw in this mass is, I treat it like mass is equal to gamma times m sub naught. Some physicists will say it's not the mass changing, but it's technically the momentum that changes. That P is equal to gamma P sub naught. I have not run into any situation where this does not hold, and I'm missing the argument about why they're saying it's not the mass changing, it's the momentum. But
what if it's both mass and momentum changing?
well, since P is equal to mv, they would have both have. If this is true, the other one has to be true. But some will claim that, well, the other's true. This is just an illusion.
Oh.
However, I'm not buying that argument. And for this scenario, yeah, we don't necessarily need that anymore. All right, so the mass is equal to m sub naught over the square root of 1 minus beta squared. I want to put it, yeah, eventually need it in terms of v. Just going to multiply both sides by this denominator, so I have mass times the square root of 1 minus v squared over c squared is equal to m sub naught. I want to get rid of that radical, square both sides. M squared times 1 minus v squared over c squared equals m sub naught. Distribute m squared minus m squared v squared over c squared is equal to m of g squared. Multiply everything by c squared to get rid of my fractions, because I don't like fractions. M squared c squared minus m squared v squared is equal to m naught squared c squared. And from there, it's just obvious it equals mc squared. Now, let's go on some pieces here. I want to, all right, so I have that there. All right, I want to do a derivative now. Derivative with respect to whatever. Recognize that over here on the right side, that's a constant. M sub naught's the rest mass. If I have an object, the rest mass is not changing. You know, we're not dealing with spontaneous combustion. We're not dealing with loss of weight and things like that. It's just an object. So when I take my derivative, well, that's a constant. So what's the derivative of a constant?
Zero.
Yeah, derivative is just change, and there's no change in a constant. C is a constant. M and V are not constants, and so we have to deal with that. So when I do my derivative, I get 0 from this equals 2mc squared dm minus 2mv squared dm minus 2vm squared dv. So you treat this bit right here, you first treat v like a constant and do the derivative with respect to m, so that's the 2 times m. And then you treat m as a constant and do the derivative with respect to v. I have 2 common to everything, and I have m common to everything. So let's get rid of some stuff. I can divide by 2, I can divide by m, I guess there's one of those. So I'm left with 0 is equal to c squared dm minus v squared dm minus vm dv. And I'm going to call that equation 1. Questions up to here? Well, I think you're about to ask something.
Yeah, but then I realized probably wouldn't. I guess there's not enough, we're not that far enough for me to figure out how much energy is in 1 kilogram of mass.
Oh, not officially yet. Well, we can get to that in a second. All right, Next. What is the relationship between work and energy? Another 131 thing?
So, if I remember correctly, work is energy over time, or energy over time, or
You're thinking of power.
power.
Yeah.
Yeah, that's power, yeah.
Force over distance?
The work energy theorem.
It's been a long time, so I don't
Okay.
remember.
Have you done a lab called Atwood's machine? Where you got a pulley here and two masses and one falls, the other one rises,
Yeah.
and you look at the change in velocity, change in speed as
I
well as
don't
change
remember
in
doing
energy.
that with the tap.
I
I think we did.
yeah, it sounds familiar. We use the little sensors to.
Yeah,
I think the work is the kinetic energy.
close, and I'll take that as close enough. The total work done is equal to the change in kinetic energy.
Oh, change.
That's called the work energy theorem. It's one of the work energy relationships, and that's what we're going to exploit right now. So I know that if I do a derivative, look at infinitesimal changes, then the infinitesimal amount of work is equal to the infinitesimal change in kinetic energy. And the infinitesimal change in work is equal to I'm gonna make a constant force times ds, which is what I have right there. Force, I know is dp dt, so this is dp dt times ds. And something you can do in calculus is remember that this is just a fraction ultimately, even though it's notation of a derivative, it's just a fraction, so I can move dt. It is a quantity, although incredibly small, I can move that dt over. So that's dp times ds dt. And what is ds dt?
V.
Yep. So this becomes v dt. And dp, so this is v times and dp, which we have right there, is mdv plus vdm. So my change in kinetic energy, my incredibly tiny change in kinetic energy, ultimately is equal to Vm dv plus v squared dm. Whoa, what a coincidence. I have it right there. So I have 0 is equal to c squared dm plus, minus this v squared dm minus vm dv. So basically I'm taking my equation 2 and I'm going to plug it into my equation 1. So I have,
It should be plus sign.
oh yes, thank you. Make sure that matches up over there. So I'm going to put this in terms of, let's see, I think that's, so I have 0 is equal to c squared dm minus dk. This ultimately traces back to dk. And so dk is equal to c squared dm. I now want to get rid of my derivatives there, my differentials officially. How do you get rid of differentials?
Integral.
Yes. And I think you said the same thing?
I said integrate.
Yeah. So we're going to integrate. Now on the left-hand side, I'm going to integrate from 0, because we're going to start it at rest, up to some final value of k. Here, m is my differential, so I'm going to integrate from m sub 0 up to whatever m is. And so here, I get k minus 0 equals c squared m minus m sub 0. Now, if you've taken a formal calculus class, where I got a differential and a limit of my integration as the same letter. Physicists do that kind of thing all the time. They just recognize they're not the same K. This is the variable K, this is a specific value K. Math people hate this notation. They will jump through hoops to avoid that. So they'll make that K prime here, or so they'll do something to make them look different. But it's physics. So this is equal to C squared M minus, let's do it more traditionally, MC squared minus M naught C squared. I'm gonna get M squared by itself, so on the left-hand side, I have K minus, or plus, M0 C squared is equal to MC squared. This K is my kinetic energy. M naught C squared is what is called rest energy. It's the energy inherent in an object just because it exists. This because it has mass. And so that is my total energy. This is equal to MC squared. And there's the derivation. So this M right here is not the rest mass. So when you're talking about what is the energy in a kilogram,
Yeah, a kilogram of mass.
is that kilogram the rest mass or is that the relativistic mass?
I thought it was rest mass.
Okay, so if it's rest mass, that means you're dealing with an object that's at rest relative to you. And so the energy would be equal to, in that case, M naught C squared, because it's not moving, so K is 0. And so that would be 1 kilogram times 3 times 10 to the 8th meters per second squared, which is 9 times 10 to the 16th joules.
So that would, what is, a 10 to the 15th, what was that, peta?
I think so.
Giga, tera is 12, 15, I think it is. Is it?
Yeah.
Peta, okay,
So that's more
90
than,
petajoules.
than the power of the Sarbama. Is that I think it was 4.148 petajoules, the Sarbama.
Sarbama?
The,
Tsar bomb, the Russian, the Soviet, the largest,
Yeah.
hydrogen bomb that was
Yeah.
ever.
Ah, okay.
yeah, so,
Thank you. Now the trick is, how do you get that 1 kilogram converted into energy like that? And that's not particularly easy.
yeah.
Sarbonga was 2 times 10 to the 17
Oh,
What are the units there?
joules.
Students, okay.
to the seven.
Split
Yeah,
out.
close. So there you are, you have an incredibly powerful bomb just sitting all around you.
Yeah, it says, thankfully, it's very inert. But then again, if we had the ability to do that, turn literally anything into energy, that would have solved the energy crisis. Solved any
It
energy
would,
crisis.
shouldn't we didn't destroy ourselves. And recognize in a hydrogen bomb, you have 2 hydrogen atoms that you slam together to create helium. When they
Yeah,
combine, they release energy, but there still has mass there, there's still left over. There's not a lot of energy released with that. One, it takes a lot of energy to get that to happen. Thus, hydrogen bombs generally have an atomic bomb in there.
yeah, I've looked that stuff up quite a bit, just out of morbid curiosity. But,
Well, all physics does lead to weapons.
then again, I think all types of science will lead to weaponry in the end. And
Yeah, I guess so.
anything can be weaponized, it's like a stapler. Not-
Yeah, that was one of those things right after 9/11, and they were cracking down on stuff that you could take in there, and there were stories that you weren't allowed to take fingernail clippers onto a plane. I don't think, you can take a mechanical pencil, but not fingernail clippers.
You're only allowed to take 4 fluid ounces of liquid. And so-
Yeah.
Yeah.
That,
The only thing I could really think of a stapler being used for is just to throw it at someone, though.
Also think that's so they can upcharge you on, like, say, a bottle of water.
Oh.
Pay $10 for a bottle of water.
It would not be
Why,
surprising.
yeah, why does
I
it
would
not
just
surprise me?
reverse the equals. That's okay.
I bought a $10 Powerade at O'Hare. That was fun.
You got scammed.
Yeah, it
It
did,
happened.
but what can you do? It's thirsty. I don't think it was that much. It was probably like $7, $8. It was still a way overpriced, but
Isn't beer in Mormon states ridiculous? Like super overpriced or something like that.
Probably.
Why would that wouldn't surprise me
There's
either
some-
in Utah.
I'm assuming that's hypothetical, because if you're not 21, then you would not know about the price of beer.
I heard it somewhere.
Okay. That's the other thing that strikes me as odd, is like, I could drink at 18, legally drink at 18, the law didn't change till after I was 21. But it's still, that gut feeling is 18-year-olds can drink. But, you know, I probably should catch up to the times one day. All right.
They can vote, they can join the military, they can
You can drink if you're in the military.
do all this other stuff.
Well, you can join the military at 17 too. That's what it
I think it's if you have your birthday.
is. It is, before you graduate boot camp.
My former stepfather-in-law joined the military when he was 15. Dad took him down to enlist right after bombing Pearl Harbor.
Oh, I've heard a lot of I've heard quite a few stories about that.
Yeah, that was
I mean, yeah,
not necessarily for publication here.